Welcome friend. In this video we shall discuss about a solubility of partially miscible liquid, and this topic is presented by me, Mr. Nahocham. A solubility of partially miscible liquid. There are four types of partially miscible liquid in two components, that is liquid in liquid system. Four type of partially miscible liquid has been formed. One type is those substance in which a liquid, that is like a example like phenols and water, in which a partially miscible liquid increase with increase in temperature. Another example is in aniline and water, aniline and hexane. So such type of liquid solution, they are partially miscible liquid and they increase their miscible characters on increasing the temperature. So above a certain temperature, the liquid become completely miscible. Example like you have this type of example can be seen in this temperature versus percentage of phenol. Example, you have water and phenol. Their partially miscible temperature is 68.1. So above this temperature, when the temperature increase more than 68.1 degrees Celsius, the solutions become completely miscible. That is type number 1. Second type of partially miscible liquid is those solutions like triethylamine and triethylamine and water, and triethylamine and water. So the solution like some substance which are partially miscible and their miscibility character increase on decreasing the temperature. When the temperature is lower, their miscibility character decrease. Example is this. So example like you have such type of example, triethylamine and water at 18.5 degrees Celsius temperature, they are partially miscible liquid. But when the temperature is below this, it becomes completely miscible and it forms one phase. Another type is you have a partially miscible or miscibility liquid solution increases on both rising as well as lowering the temperature in certain range. Example like such type of partially miscibles can be seen in water plus nicotine solution, water plus beta picoline. So On increasing the temperature, they also increase, and decreasing the temperature, they can decrease their miscible. So the solution like water and nicotine liquid pair so completely miscible when put above or below a certain temperature. And fourth type is ether and water. This is one type of example, like those in which a complete miscibility temperature cannot be obtained. They remain partially in nature. So they cannot be affected by temperature on increasing or decreasing the temperature. So the solubility of partially miscible liquid are categorized into four types. You can push the video and look here. I have written here the four types of partially miscible liquid system have been observed. These are: number one, those in which the partially miscibility increases on increasing the temperature. It can be seen in the solutions like phenol and water, aniline and water, aniline and hexane, ethanol, methanol and carbon disulfide, cyclohexane and methanol system. So, at and above a certain temperature, a liquid becomes completely miscible. Type number 2 is those liquid system in which partially miscibility increase on lowering the temperature. Example like triethylamine and water system, triethylamine and water system. At and up below a certain temperature the two liquid become completely miscible. Type number 3 is those in which a partially miscibility increase on both rising as well as lowering the temperature in certain range. Example as water and nicotine, water and beta-picoline system. So this liquid pair shows complete miscibility both above and below a certain temperature. Type number 4, those in which complete miscibility temperature cannot be obtained. A common example is ether and water system. So these are the four solubility of partially miscible liquids. As we've discussed, these are the four types. Critical solution temperature, CST. So the temperature above or below which a pair of partially miscible liquid become miscible in all proportion is called critical solution temperature, or it can also be called consolute temperature. So some liquid pairs are completely miscible above a certain temperature. It can be seen in a phenol and water. Phenol and water, like, they become completely miscible. Example like phenol and water, 68.1 is the partially miscible temperature. So above this temperature, they become completely miscible and form a one-phase homogeneous solution. So the certain range of temperature can be seen in some liquid like phenols and water pair that become completely miscibility above a certain range in which a which is said to be upper critical solution temperature. Whereas some liquid like in diethylamine and triethylamine in water, some liquid pair so completely miscible below a certain temperature. These are called LCST, lower critical solution temperature. The temperature above or below which a certain pair of partially miscible liquid become miscible in all proportion is said to be critical solution temperature, or it can be also called consolid temperature for the pair. As we've seen in some phenols and water solution, some liquid pair like phenols and water, they attain completely miscible above at 68.1 degrees Celsius. So in which case they are said to have a upper critical solution temperature. Well, some liquid pair show complete miscibility below a certain temperature, which are said to be lower critical solution temperature LCST. But on the other hand, some liquid pairs show both lower critical solution temperature as well as upper critical solution temperature. Some solution can show both the temperature. All partially miscible liquid pair have in general an upper or lower CST. However, the upper CST cannot be realized if one or both component boils out before it has been reached, and a lower CST may not be observed if one or both the component is freezing out before it is reached. Thus, under certain atmospheric conditions, none of the CST is observed in ether and water solution. So the temperature cannot be affected on this ether and water solution. So these are some critical solution temperature. Water and phenol system, their upper critical solution temperature is 68.1 degrees Celsius. So above this, the component become completely miscible, and cyclohexane is 49 points. Cyclohexane and methanol, it has 49.0 degrees Celsius upper critical system solution temperature. So the above this, the solution become completely miscible. Similarly, in this case, methanol and carbon disulfate 49.5, above this temperature it become completely miscible. So in solution like this, water and diethylamine, they have a lower critical solution temperature. Below this temperature 42.0, they become completely miscible, and below this 18.5, this solution become completely miscible. So water and nicotine, they show both the upper and lower critical solution temperature. It is written, you can push and look. So some amount of impurities may also produce large changes in the critical solution temperature. Suppose you have a component A and B, that means liquid A and liquid B. The normal variation temperature is 50, but when the impurity is present in the solution, their critical solution temperature increase due to the presence of some impurities in the solution. But this type of solutions, the impurity can be observed by a test. A test is known as Kramer test. This observation forms the basis of Kramer test, which can detect and measure the minute quantities of impurities that vary in the temperatures in the liquid-liquid system of solution. It is found that the change in the CST value in the linear function of the concentration of the impurity. Variation of mutual miscibility of phenols and phenol system. This is one type of mixture when phenols and water mix. So when phenol and water, that is both are liquid and liquid, are mixed, they are partially miscible at ordinary temperature. So by stirring or shaking the two component liquid, that is phenol and water, become saturated solution at different composition are obtained. So let us draw a temperature versus percentage of phenol, percentage of phenol versus temperature. So a graph is plot and between A, C and B. This is temperature in degrees Celsius. A line is joined, horizontal line is drawn and joining these two graphs, and let us mark A and B. And this Y, the point Y, and the middle point is indicated somewhere here. This point, this is X. So this joint conjugate solutions, this point is tie line. So the Y and Y thus, this Y, the point Y is phenol in water solution, and Y thus is water in phenol solution. So this X is a tie line, it is a conjugate solution. So at certain temperature, the two conjugate change into one homogeneous solution. So if we see the graph, the phenols and water are only partially miscible at ordinary temperature. Therefore, the solution need to be shaken. So while shaken, the water and phenols, that is two liquid with each other, a two saturated solution of different compositions, one on the phenol in water and one in the water in phenol, are obtained, and the line is joined by a saturated conjugated solution, that is tie line X has been drawn. So the mutual solubility, the mutual solubility of phenol and water increase on rising the temperature. On rising the temperature, let's say this point is 68.1. Ultimately, at certain temperature, the solubility and miscibility increase on increasing the temperature. So on reaching a certain point of temperature, they become completely miscible. So above this 68.1 degrees Celsius, at the time the 36.1% of phenols has been added, and water is 63. I'm writing here 63.90%. So above this degree Celsius, the two solubility the partially soluble liquid become completely miscible and form a homogeneous solution. This part, homogeneous solution, completely miscibles and deform homogeneous solution. So it has been found that the critical solution temperature is 68.1 degrees Celsius and the percentage of phenol is 36.1, water is 63.90. So the composition of the solution has been formed use this much, and above this temperature the two liquid that means solid phenols and water, above this temperature the two liquid become miscible with each other in all proportion and deform homogeneously. So the variable, this is the variation of mutual solubility of water and phenol with temperature graph. This is a type 1, and another type is aniline and hexane. Aniline and hexane system. Aniline and hexane system, the behavior of aniline and hexane system is similar to that of the phenol and water system. The consolate temperature in this case is 59.6 degrees Celsius. The composition of solution is 52% aniline and 48% hexane. So the critical solution temperature is 59.6 degrees Celsius and percentage is of aniline used in the solution is 52. Hexane is 48. So this type of solution, aniline and hexane, is somehow like phenols and water solution. Above this 59.6 degrees Celsius, the solution become completely miscible. Some other pairs of liquid which are partially miscible at ordinary temperature and become completely miscible on rising the temperature are water and aniline, aniline and benzene, carbon disulfide and methyl alcohol, etc. So all this type of liquid pair has the same properties. The consolate temperature of these three systems, all these three, water and aniline and benzene, carbon disulfide and methylene alcohol, they have a consolate temperature at 167 degrees Celsius and the percentage is 59.6 and 40.5 degrees Celsius respectively. Suppose water and aniline, if you are studying the water and aniline, so their miscibility, partially miscibility temperature is 167 degrees Celsius and water is 59.6% and aniline is 40.5. Yes, water and aniline is this much temperature and aniline and benzene is 59.6 degrees Celsius and carbon disulfide and methyl alcohol, their critical solution temperature is 40.5 degrees Celsius respectively. So above this temperature, the two miscibility liquid become completely miscible. So this is all about the aniline and hexane system and some other types of upper critical system, upper critical solution temperature. Okay, another types of mutual miscibility graph that is a triethylamine. So similarly, a graph is plotted between temperature versus triethylamine in percentage. Say 0, and when you reach here it is 100%. So this is a temperature in degrees Celsius. So the triethylamine and water system constitute a system in which a mutually miscibility or mutually solubility increase with decreasing the temperature. So their lower critical solution temperature, the mutual solubility of these two liquid, triethylamine and water system, the graph is plotted here. So a graph is plotted here, and their lower critical solution temperature is 18.5. This is their LCST temperature in degrees Celsius. So their consolidate temperature is 18.5 degrees Celsius. At this point, at this temperature, they become partially miscible. But above this temperature, when the temperature is increased more than this, above this, the liquid give a two phase. They become a two phase. That means immiscible. And below this temperature, they become completely miscible and give one phase. So this is triethylamine and water system. They increase with increasing the temperature, and below this consolidate temperature, they become one phase. So this is also very simple to understand. Another type of liquid system, that is nicotine and water system. A graph is plotted between the temperature in degrees Celsius and mark here 0, 100 and percentage of nicotine. So nicotine and water graph is shown here. Figure this nicotine and water system is shown here. Nicotine and water show an upper as well as lower critical system temperature. This solution shows both the upper critical system temperature and lower critical system temperature. So between these two, they are partially miscible. So in other words, we can say that these two liquids, that is nicotine and water, these two liquids are completely miscible at above a certain temperature, and below they become one phase. So a temperature between 208, that is from here, and this is a 60, 208. So between these two range, between the range of 208 to 60 degrees Celsius, they are partially miscible. In nicotine and water solution system, a temperature range between 60 degrees Celsius to 208 degrees Celsius. Between this range, the solution is partially miscible. So when the temperature cross more than 208 degrees Celsius, the partially miscible become miscible, completely miscible, and form one phase. So similarly, when the temperature is lower, less than 60 degrees Celsius, again they become completely miscible in one phase. So nicotine and water, such type of system can be seen both type of temperature, both type of critical system temperature is seen. So eventually the upper consolidate temperature, that is 208, and the lower is lower critical solution temperature, that is the consolidate temperature is 60 degrees Celsius here. So the between these two temperature, the mixture of water and nicotine will appear two layer. Two layer is like this, something like this. It can be visible in two layer at the temperature range between 208 to 60 degrees Celsius. But when the temperature cross 208, it become only one type of solution, homogeneous type of solution can be seen. Similarly, when the temperature is below 60 degrees, a one type of solution layer can be seen. So this is the nicotine and water system temperature. So this is all about your partially solubility of partially miscible liquid and the effect of temperature in the liquid-liquid solution. So you must be able to define what is CST, difference between upper critical or solution temperature and lower critical solution temperature, Tye-Lie, Christmas test, all this thing. So that's all for this video. Thank you everyone for watching. Thank you.